So in addition to decision trees that are fit on regression problems, so on continuous data, we can also fit classification trees. And so this is going to be very similar to a regression tree, except it's used to predict a qualitative response rather than a quantitative one, so a categorical response. And we predict that each observation basically belongs to the most commonly occurring class of the training observations in a given region. So that's how the predictions occur. You fit this tree, and then if you got a new observation, you would say that it belongs to the most commonly occurring class of the training observations that match that region. So we use recursive binary splitting to grow the tree. And instead of residual sum of squares, we can use something known as a Gini Index. And so this is going to be the equation for that. And so it's basically a measure of the total variance across k classes. And so if all of these p hat mk values are close to 0 or 1, then this is going to be really small. And so essentially it measures the node purity. Small values indicate that the node contains predominantly observations from a single class. So if most of the observations are from the same class, then it's going to have smaller values. And so in R, this can be estimated using the gain underscore capture function. And so, for example, here, if let's say I'm trying to classify whether or not someone has heart disease. And so I've got some data that consists of 303 patients, and we're classifying whether they have heart disease based on 13 predictors, including age, sex, cholesterol, things like that. And so here are the steps that I would do to fit this classification tree. First, I would split the data into a cross-validation set. So for example, here I'm doing 5-fold cross-validation. My data set is called heart, and so I split those into those 5 folds. Oh, I gave this away. How many folds do I have? 5. And then I'm going to create a model specification that tunes based on complexity, alpha. And so I'm still fitting my decision tree in a very similar way to the ones that we looked at before, except now the big difference is my mode is classification. So you have to tell R what mode you're interested in here, and I'm going to say it's classification. Because in this case, I'm classifying you into categories either having heart disease or not. And then you fit the model on the cross-validation set. So I'm using tune underscore grid here, and I fit my model. So I plug in that tree spec that has the specification that includes it. This is classification. HD is whether or not someone has heart disease. These are my predictors. I'm using a grid to look at different cost complexities. I set my resamples to that cross-validation set. And then finally here for metrics, you can set the metrics you'd like to use. For example, I would like this to output a set of metrics. So that's what this metrics underscore set says. And I want to output gain, capture, and accuracy. So what alphas am I trying here? I'm trying 0.01 to 0.05 by 0.01. So 0.01, 0.02, 0.03, 0.04, and 0.05. Okay, so and then once you've done that, the fifth step is going to be to choose the alpha that minimizes the Gini index. And so I can use this select underscore best function, and I'm going to set my metric equal to gain capture, and then I'm going to pull out that best value. So what this is doing is it's taking my model, it's selecting the best metric, and then I'm pulling out what that best value actually is. And now I'm going to fit the final model, so I'm going to fit the final specification. And so I'm going to have all the same pieces in this final specification, except now for cost complexity, instead of tuning that, I'm going to plug in best, which is the value I just pulled from the select best function. And then I can fit this final model using this final specification. And then we can examine how the final model does on the full sample. So for example, we could predict using that full sample. And so I'm going to predict what the values would have, what the training values would be using this model. And then I can do what's called a confusion matrix. So this confusion matrix is going to show us the truth versus the prediction. So the x-axis here is truth, yes or no. Y-axis is prediction, yes or no. And so where we were correctly classifying is going to be where the prediction is yes and the truth is yes, and where we're incorrectly classifying is going to be where the prediction is yes and the truth is no, or the prediction is no and the truth is yes, for example. So, okay, pros and cons of decision trees. The pros are that they're simple and they're easy to interpret. The cons is that they're not often competitive in terms of prediction accuracy. But next class, we're actually going to be discussing how to combine multiple trees, and this will really improve that accuracy and make them kind of much better in terms of being competitive in that way.